not necessarily all of them are doing the research work, but trying to apply it in their domain. So we'll see how the Spark Cognition, they've been able to make use of it. And then, okay, so before we go deep into the other area, this is our Meetup announcements and kind of what do we have upcoming. We have next Meetup scheduled December 12. Please do sign up. This is going to be an AI, it's a panel discussion on AI top, what is that? Advancement in AI field in 2019. Very recent developments that's been going on, mostly covering the vision area. That's where some of the IBM chip scientist, I'm sorry, missing the title. Chip design architect gonna be there. He's gonna be the panel moderator, and we're trying to get some outside folks also tied in. But stay tuned; it should be really exciting. And about our next year meetup, that's kind of still out there. I'm trying to get together both the speakers, funding, and everything. So planning for that. If you want to sponsor, of course, we have Spark Cognition been generous to us, hoping they will continue. And then Capital Factory, they've been giving us the venue for, we still have it for next year, so that's good. And there are some other events we're trying to plan together, but never materialize. But hopefully we'll get to that next year. About today's meetup, Spark Cognition is the food and sponsor of the food. Big clap for them. Thank you. And of course the speaker is gonna be from their area of development and research work. Capital Factory giving us the venue. What else? We are also been encouraging lightning talk. That's essentially if you are just want to speak up current work, 5-10 minutes, don't want to take a long, you don't have a like big thing to discuss, that's also fine. We can kind of squeeze you in. So keep that in mind if you have something you want to share with us. We are working as a non-profit organization. We just got 501(c) this year, so that's good, and that helps us kind of get the funding and also arrange it in a better way. So with that, I'll hand it over to today's speaker. She is Jashmi Legisetti. Sorry, hope I pronounce it right. So yeah, obviously she is working in the cutting edge area of NLP and working as a data scientist in Spark Cognition, working cool stuff with computer vision and social media mining. So instead of me talking about her, let me call her to the stage and let her introduce herself and her work. Thank you.
All right. Hi, everybody. Thank you for making time to be here. I'm really excited to see new faces, and it's delightfully nice to see old faces too. And okay, I think I need to pause this. Just a second, technical difference. Yeah, I think the traffic is really bad today. I didn't know this is how downtown is, so it generally takes like 15 minutes to get here, but it took me 45 minutes. Then I just realized that all the RSVPs are not going to be true to the number. But it's okay. I'm really happy that you guys made it on time. Cool. So today I'm talking about NLP and machine learning in Austin's Big Data AI Meetup. and this sentence has more buzzwords than the normal English words. So I thought I could probably start with a ELI5 version of each big word on the screen. All right, cool. So what is AI? AI is it's like a science that is teaching a machine to mimic human behavior. Like we're trying to perceive how humans can visualize things or hear speech or look at data and understand what it's trying to say, or it's more like mimicking human behavior. And it's I know you've seen movies like Blade Runner or like Matrix. We are not there yet, but we're trying to embrace AI to do cool things like automating engineering work or trying to make money out of business value or business propositions. And ML is machine learning, and it's a subset of AI where it focuses on the ability of machines to receive a set of data and learn about data, and all these algorithms are trying to focus on seeing how data can be processed and how we can harvest information. And we have a human in the loop who creates machine learning models to make the machine understand how to perceive things. And big data is, as you can see, it's like a large amount of data, and today there are a lot of data engineers working in this domain to access complex data or streamline it or make it bridge them between development and deployment. And then comes NLP. That's the main topic that I'm going to talk about. It's all about leveraging tools and techniques and algorithm to process and understand natural language. And natural language can be in the form of text or speech. It's something like it's like how Han Solo can understand Chewbacca. Nobody else can, but Han Solo can. So it's like developing a bond between the computer and text. Brace yourself. There's so many movie analogies coming up. All right, what's next? Okay, so today's topic is knowledge extraction using similarity. I know it sounds complicated, so let me just break down what each word means. What is knowledge extraction? So it's all about making your unstructured data more analyzable. And what do we mean by unstructured data? So we have data in real life, which most of our engineers use SQL to access, and they work on it. So all this data, which can be tabulated in columns and rows or tables, is called structured data. But all these other sorts of data that you cannot have a predefined model or data model to store this information. And this is typically text-heavy information, like reviews on Amazon or opinions of movie critics, or just blogs about sports or politics. So you have information which is very verbose and it's detailed, but you really don't know how to save that information. And this is a really important business value, because a lot of companies which are aiming at B2C rely on customer information and their opinions, and they try to make money out of it. And so that's unstructured data for you. And what does knowledge extraction do? Let me give you an example. Maybe everyone would have heard about entity extraction, where you have defined categories and you're trying to extract information, but knowledge extraction is different. And how is that different? For example, say you have your finals tomorrow and you're not prepared. You grab your book, you grab your highlighter, and you try to highlight everything that's important to you. When you open the book, you really don't know what you're looking for, but when you open the page, you're like, oh cool, I think this is important, this sounds important, this looks important, and you just keep highlighting that. So that is the knowledge that you're trying to extract from your book, though you really don't know what you're looking for. So when you have large amounts of data and you want to get insights or business values from it, you use this concept of knowledge extraction. And it's actually, technically speaking, it's a combination of pattern-based machine learning techniques to teach the machines how to extract information. And when you can do that, and the whole idea is to automate this process so that you can iteratively validate your data and make it more analyzable. And coming to the types of data. So when you think of data, people who are new to machine learning are going to think of Kaggle, when you have big data sets of a particular domain where you're trying to solve a business problem. But the thing is that Kaggle data is really, really clean and processable. But when you come to real life, data is definitely messy, and there's so many missing values. For example, the data that we get from our customers can be in any form. So speaking of unstructured data, it can be in the form of reports, press releases, PDFs, technical logs, data sheets, instruction manuals. And each of these data types have their own constraints. Like reports have like a regular way of placing the information. Press releases is just like a short paragraph of the information. You're trying to make a story out of it, but you just have like short sequences. And PDFs, again, you have like alignment differences. And technical logs have a lot of handwritten information. Not all that information can be converted to usable information. Most of it is lost in like translation. And data sheets have a lot of precise and important information, but they are stored in the form of tables. So you have like an other step on top of extracting data to look at tables and get the information from tables. And they also include images, and the images have sub-images, and the sub-images have text. So there's like levels of information collection, and that is not super direct. You need to process that to understand where this whole equation of data processing fits in your big picture. And instruction manuals, they have multiple columns, multiple subcolumns, and each column has either data or image. And if you're trying to understand more about the data, having an image really helps because it's complementing the information present in your caption. Like, you know, how like when social media mining is done, they try to extract the caption of Instagram picture and the comments within because it kind of complements the whole information chain. Cool. Let's move on to the next one. So as of today, we have many open source NLP libraries out there. One is GenSim, one is Pacey, and the other one is Glove Embedding or NLTK. And they are super smart. They are placed in a way that they can take in commercial data or publicly available data and make sense of that. So when we come to NER, what is NER trying to say is that when you try to tokenize a sentence, like break the sentence into words, you can assign each word to a predefined category. Like the first sentence, it says Apple is looking at buying UK startup for 1 million. So based on the knowledge of previous data, the library knows that Apple is an organization, UK is a geolocation, and 1 million means money. But when it comes to customer data, or like when you're trying to solve a business problem or like a real life problem, you do not have predefined categories for domain-specific data. For example, the second line, it says LWA, and I really don't know what LWA means, and it's something like a sensor, I guess, and the offerings are offered from some range. So the point is that range is an entity that you and I will not know until you read a paragraph about the sensors. For example, this one. You really don't know what it is, but once you read the paragraph, you're like, oh, probably this is a feature of the paragraph. Like that LWA probably stands for product and blah, 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 blah. And that range 125 to 100 meters, it's probably like some specification about the sensor and things like resolution. And when you're trying to find common features between products, it's like, you know, you don't really know what is important, but when you're comparing products, you'll know what is the important feature. Like say you're trying to buy a particular, like a hair dryer on Amazon. The first thing that everyone would want to compare is the price, probably then the specification, then what's the voltage thing. So all these things you don't know are important, but when you compare products, you'll know those are important. So we're trying to cache on that particular thing where you find similarities in your data based on other data in your history. And based on that, this is how you extract your custom entities. So now you look at all the data in all the reports in your historical data, and you see like, okay, I got a list of products, and I got a list of ranges, and I got a list of vendors, and I got a list of resolutions. And then based on this clustered information of custom entities, you can probably label that and you can add it to your library, saying that next time when you see something like this, tell me that you found a product. And probably then I can be like, hey, the business value in this is that I can talk more about the products and I can tell you more information about that, and that's going to lead to more customer insights. The next thing, but what are the challenges in this? The thing is that when you have publicly available data, it's super clean, and it's a large amount of data. But when you have customer data, they are very, very specific about the amount of data that they share with you. One reason is for legal reasons, and the other one is that probably they're just trying to see how a POC can be made, and then they'll probably invest in that. The whole idea is that when you're trying to make a primitive model, you need a large amount of data to train this model, but you got to make the best of the situation. And how do you do that? You try to follow methods in a way that you can actually find relations in your data with a lot of missing values. And the second challenge is that your sequences or your phrases are super short. When you're trying to make something from a story, it's nice to know the context within. But if it's super short, it's hard to know how the story is leading or how this particular feature is important to the product. And then they have weird formats. Like I was talking about the technical logs, they have a lot of handwritten information. For example, the other day we had technical logs from an aviation company, and a lot of places where they try to describe the problem, the technicians used to just say okay or done. And we don't have a solution from that, but we just know that it means it's done. So you're trying to find information, though the result or the inference is completely not in the right format. And then the best way you can do is try to group similar data to like make custom entities. And the other one is that you have NER models like Spacey, as I mentioned, but they don't perform well on domain-specific data. So how do we overcome all these challenges? So we use Similarity Search. So it's like the best thing about using Similarity Search is that you don't need label data. And label data, it's like the most wanted information for a data scientist. And it's really hard to score label data. So this particular mechanism doesn't need label data at all. And you're trying to search for a pattern in enriched data. I'll tell you more about what enriched data is. And the next thing is that you try to find sentences from your corpus, like from your data set, which are similar to a given sequence. So say I'm talking about a particular hair dryer or a particular product which is related to a sensor. You're trying to find information that is very similar to that. And domain-specific extraction is done in a very semantically and syntactically meaning way. I'll tell you more about this when I tell you about the model. And as I said, it's completely unsupervised, so you don't need any label data in this. So how do you do this model? So we use a combination of autoencoders and sequence-to-sequence model. What does an autoencoder do? So say you're trying to get some information from a data, and you have a large search space. As an engineer or as a person in engineering field or like a business company, you'd be like, oh, searching is really hard, but I want to get to the data as soon as possible without actually going through loops of information, and I do not need lags in this process. So how do you do that? So we use an autoencoder model to get like an extremely rich semantic latent space. So when you give a large size of input, it condenses to a compressed feature vector. And this vector is like the cream of information. So it's like all your information has reached a nirvana stage where every piece of data is converted to a vector, and each vector knows the semantics of the other vectors. So if you want to find things that are very similar to each other, what you got to do is do a mathematical operation of just finding the most similar vectors in that space. So mathematically speaking, you can take like a dot product, like a cosine similarity, and you can find the closest vector. So if I'm talking about, hey, this hairdryer is $49, and there's another sentence that says that $50 is too pricey for a hairdryer, it's going to find similarity in that sense because it's talking about the same product, it's talking about the same value range, and so you know that those are similar opinions about this particular product. And then you can use your cosine similarity to rank your sequences, because oftentimes they talk about the same thing, but say it doesn't actually make sense. So probably they're talking about a hairdryer, but they're praising about it, but you're trying to find negative sentiment in it. So you try to find the closest cosine similarity based vector to each other. And it's highly scalable for performing search. So it's faster than using a hash function. It's faster than nlogin. So so when you try to deploy models in a B2C environment, time is money. So if you can do a very efficient search space, half the battle is solved, because you don't want to lose customers based on lag, right? So this is like a really nice way of compressing your feature vector in the right search space. All right, so what is a sequence model? So in today's, yeah.
Quick question. So the autoencoder
Yeah.
you're doing, is that like domain-specific pre-built model, or you're using like off-the-shelf autoencoder?
You can use off-the-shelf, like you have predefined methodologies of building an autoencoder, but you can always hyper-tune the parameters according to the data set that you want, or the way you want your latent space to be structured. But the mechanism or the model of the entire process is going to be the same. So it's like the skeleton is the same, but you're going to add features to it.
But you train it.
Yeah, you train it on your data set. You don't train it on external data set. Sure, thanks. Cool. So the next thing is sequence-to-sequence model. So what is a sequence-to-sequence model? So in today's world, this is a very, very common thing. Google uses it, Amazon uses it. Almost every phone that uses speech recognition uses this. So what it's trying to do is it's trying to map a sequence to another sequence. So like if you're doing a translation, how are you to another language, it's going to map the feature vector of English to, like, say, Chinese. And the interesting thing about this is that your vectors can be of different shapes, but the latent vector or the immediate vector or the hidden state vector is going to be of the same size. The point that I'm trying to say is that in the mechanism of translation, the whole process of converting into mathematical vectors is completely resolved to just like point system. And video captioning. So when you give an image, you get a sentence. So that's also converting a sequence of bytes to a sequence of words. And speech recognition, it's converting speech to text. So it's another sequence in the form of a compressed sequence. Okay, so how do you design this? So we have a cascaded model of LSTM cells. What is an LSTM? Okay, let me know if you have questions, because this is the part where it gets super technical. So LSTM is like long short-term memory. And the gist of it is that it can understand temporal data and it can understand sequential data over time. For example, if I ask you, hey, do you know the 17th letter in the alphabet song? In your head, you'll be like, nope, I don't know it at the top of my head, but if I sing it in my head, I'll probably get to know it. So this is how the information is stored. It's stored in the form of sequences. So when somebody says, hi, how are you? They're not going to understand the meaning of are or you. They're going to understand how this whole thing makes sense in a contextual form. So for example, you ask me, is 4 enough? I'll be like, 4 energy bars? Probably not. But 4 murders, yes, they are a lot. So you're trying to understand the context of your information before you understand the information as such. And how is this modeled in machine learning? So you have the green boxes are the encoder boxes, and the blue ones are decoder boxes. So all of them are LSTM cells. So what it tries to do is it takes in an input at time t1, appends the hidden state input, and then proceeds to the next one. So at every time it updates the hidden vector, it updates the current word by making it rich in context every step. So at the end of the encoder, you have like a vocabulary of words. It's like trying to understand how this person is speaking or which language the person is speaking. For example, if you try to train the encoder on the way people speak in like Minnesota, it's going to be different from the way people speak in Texas, because the syllables are the same, but the way it's pronounced or the way words are placed together is completely different. And the decoder's function is to take this context representation from the encoder and generate an answer. It predicts the next word with the help of the hidden vector of the previous word and from the encoder. And mathematically speaking, it's going to have like a softmax layer which can pick a word from a probability distribution of words. So it's just trying to say that so when somebody asks you, hi, how are you? It's going to reply, I am good. I am good are 3 words, and they're not going to come individually. They're going to come as a sequence. It's going to take from a distribution of data and go like, okay, the next step being I makes more sense than saying good before saying I. So it forms a sequence of data based on a probability distribution of words. All right. So what is the meaning of the combination of this? So we form an ensemble-based encoder method which uses a sequence-to-sequence model. So you take an autoencoder to form this semantically rich latent space, which is super condensed, and you give that as a representation. So the whole idea of combining these two models means that you're trying to reduce the space where your search can be done, and you're using really, really less amount of information to make another prediction. So it's going to be super fast, it's going to be super precise, and it's computationally less expensive. So it's like a whole deal which is super efficient. The next one is, what can we do with this model? So at this point, we're using this model to do some sort of question answering in our work, and we can also answer questions which are related to like factoid-based questions like what is it or where is it or who type questions. And another feature would be that you can use RNN-based networks which support bidirectional attention flow. I know these words sound big, but I'm going to talk more about it. And also you can hypertune your parameters where you can, so there's this big problem when you use LSTM cells. It's called exploring gradients. So you can avoid it by like hypertuning your parameters. Cool. So I'll tell you a little bit about our team. So I work for Deep NLP. That's like an NLP-based team in Spark Cognition. And what do we do here? We try to make unstructured data more analyzable, as I said. And the next thing in the data science part of Deep NLP, we're trying to do something called document understanding. So generally, when you're trying to process text in PDFs, you have efficient tools that take in a PDF and give you the entire data. But when it comes to tables or images, it completely skips it because it can't actually locate the text within. So now we have like mechanisms to process a table, find the grid lines, find the cells, and try to do key value pair mapping. For example, this one, when you say that I have an ordered date of say February 26th, it's going to give you like, oh, cool, the item that you ordered on that day is pen. So it's basically trying to join a column name to a row name. And this is not straight out of the box because you have like other sites like which look at tables and get information, but they use template-based data. What I'm trying to say is that they have predefined ways of extracting information from the table because they know that this table is always going to have date in the first column and the information is going to be in the third column. And we are not trying to hard code it. If you try to hard code it, it'll be like a big flop when you try to take new tables. So there's no one size fits all. So you're trying to use machine learning models to make this happen. And we have invoices and we have wonky tables like that, which actually don't make sense to me. But it makes sense to the model. So you're trying to communicate most significant results in the form of a table by just using a key value pair rather than a big fat piece of table. All right. So this is an example of an invoice. As of today, we have like websites like bill.com that take in this invoice and give you like, oh, cool, this is an invoice by a vendor, so I'm going to give you the balance due. The idea over there is that they use templates again, so they're going to be like, find me the amount in the information where it's next to balance. But the idea is that if you try to use this and there's another invoice where the balance is below and not to the right of it, it completely fails. So you're trying to learn more about the proximity of the word rather than the position of the word. You're trying to see how relevant the words are next to the word balance rather than saying, okay, give me whatever is to the right of the word. Cool. So that is what we do in Deep NLP, but I thought that I could take some time to talk about what's new in NLP. And if you have any questions, please let me know. I'll just like skim through it. And okay, the cool thing in NLP that came out in 2018 was actually big for NLP. There were super cool models that many companies like Google and Facebook came up with, and TensorFlow is booming. It's always coming up with something new, and many people are trying to use that in deployment, and they try to deploy the models to cloud. So a lot is happening, just not in the academic sector, but also in the industry sector. Okay, what does attention mean? Let me give you an analogy. Okay. My dad's not a big fan of superhero movies, but when I tell him like, hey dad, there's this superhero, there's this nemesis, and then they have this huge fight and New York is destroyed again, and then he's like, wait, who is Thanos? So I'm like, no dad, pay attention. So we have something like that prompts the model saying that, okay, you got to pay attention to this particular word because it matters a lot to the story. So that's called a context vector. So you see those squiggly red lines? It's basically forming a weighted sum of annotations of each word. So it tells you which word is the most important in this particular story. And we have something called a feed-forward alignment model, which scores how well the inputs and outputs match together. And this is how you know which word to pay attention to. Cool. And the next one is BERT. So in 2018, from Jan to May, we had like an explosion of Sesame Street models. We had BERT, we had Elmo, and the whole idea is that we have these language models. So in the past, we had something called word2vec, where you can like represent a word in the form of a numerical vector, and you'd be like, oh, cool, I can find other words based on this vector. But the thing is that was so 2015, I guess. So in 2019, what they came up with is like a statistical model of understanding a vocabulary, not just based on each word, but based on the context of the word. So Elmo learns the context of the word based on the previous word and the next word from right to left and left to right. But BERT, it came up with another level of clearance that it learns every sentence from right to left. So if I'm trying to say, let's add this in the skit, it's going to learn the sequence from right to left, left to right, and it's also going to be like, if I try to stick to this sequence, I'm going to, overfit the model by learning the words in the bidirectional flow. So what it does is it tries to mask the whole sentence by just eliminating 15% of the sentence. So now you have a sentence with 15% of the information missing. And BERT model has an encoder that can predict that missing 15%. So what it's trying to do is it's eliminating a bit of the vocabulary so that it can get smarter in learning that language. And on top of this vocabulary of the encoder, you add a classification layer to the encoder output, and then you multiply that with like an embedding matrix. Okay, basically each operation that I'm mentioning in mathematical terms, it basically means that you're building a dimension which is purely based on the vocabulary of the language and not exactly the sentences used. So it's like how a child learns English based on a course of time, but it doesn't necessarily mean that he knows each and every word, but he knows it based on the context. So probably like you'll come across children using new words which they haven't actually learned. They just try to understand the context of it based on like conversations. So even if you're missing a word in the language, it knows that that's going to be part of this vocabulary. And the next step is that it tries to calculate the probability of each word by using a softmax layer. So this one is actually used for understanding words in English language. And another example of BERT is used for sentence classification, where you can give a sentence and be like, okay, tell me if it's spam or not spam. I know as of today, we have other models like Naive Bayes, or we have SVM models to do this classification. But the reason that BERT is more popular is that it can be deployed to any network by just using the out-of-the-box BERT model. You don't really require to train it on another data set. And the nice feature about BERT is that it's completely design in TensorFlow. And in order to deploy this model, it just takes 6 sentences. And that is super cool when it comes to like understanding more about customer data. Because in the end, we are using machine learning. Okay, what is machine learning? Machine learning is just like a love child of math and business value. So if you're trying to make money out of math, you got to use machine learning. So BERT model makes things more efficient because computationally it's less expensive and it's already more efficient. So you don't need data for that. Cool.
Quick question, sir. You can use it on sentence. Have you tried using it on documents, or how large can it handle?
Oh yeah. So the thing is that you can design your sizes of the dimensions of your input and output vectors, and each document is divided into spans, and the spans are divided into like sentences. So you give like a whole sequence as an input. Like in previous sequence model, you give word by word, but over here you just give sentences. So it's just like you're not going through every word, but you're going through every sentence, and that reduces your computation drastically. That's going to consider a sentence as a whole.
I was trying to see, like, is that like, can it be, is it a good classifier for documents?
Yeah, it's a good classifier documents. So it's basically, yeah, you can use it for sentences, you can use it for documents, or you can use it for words. So it's very versatile in that way. So it's like learning a language, and you can segment it any way you want.
Have you worked with doc-to-vec? You mentioned word-to-vec.
Mm-hmm.
Is that
So word-to-vec and doc-to-vec are a way of representing a file using just numbers. But over here, you're representing a language using a distribution. So that makes it more smarter to understand what comes in the sequence, how does this word fit in the context, or how can I make another sentence or generate another prediction. So you're not sticking to the vocabulary or the words that you know. Like word-to-vec and doc-to-vec, they literally map a single word like Apple organization to a mathematical vector. So if according to doc-to-vec, Apple is just going to be a dimension of 512 size dimension of numbers. But over here, it's going to be a matrix to understand the context of the word and the way it fits into the language. So you're learning the distribution of how the vocabulary is based. Cool. Okay, next. The next big thing in NLP is something called use. It's a universal sentence encoder, and it encodes the text into something like a higher dimensional vector, and this can be used for text classification, semantic similarity, clustering, and other NLP tasks. The model is trained and optimized for like using words that are greater than a word, like just not like short sequences or phrases or paragraphs, but something which is greater than that, like sentence level. But the best thing about use and why it's more popular is that it is interchangeable between languages. So right now you have GenSim or NLTK that use only English vocabulary, but if you're trying to implement something in Arabic or Spanish, it's really hard because every language has its own constraints. Like basically the languages in the Orient have a lot of syllables, and a single change in the syllable, it negates the whole meaning of the word. But that's not how it is in English. So it's very crucial that you learn a mapping between different languages and just not the language itself. So use vectors are like, just think of it as like word-to-vec, but in like a universal form, where you can use the same vector in Arabic or English or like Spanish. And they have limited languages, but it's cool that it can be transferable. Cool, these are the references that I used. And yeah, thank you. Any questions? Can you use this? Yeah, I think he has a question. Go ahead.
Thanks very much for your presentation.
Thank you.
I was wondering if you've seen any or like worked on any kind of modeling relating to kind of applying doubt or subtext to any of these documents analysis.
Are you saying like a subtext to like a summary of a document to describe the document? Is that?
No, like kind of applying a question as to whether what's represented is in fact true.
Can you give me an example?
Like, I mean, like any information can be presented, but obviously you need some kind of context for some kind of doubt. But have you seen any models that kind of are focusing on that at all, or trying to tease that out?
Okay, so if you're saying, are there any question answering models that answer quick questions? Is that what you're trying to say? Like subtext?
No,
right?
just anyone can make a representation by stating something, but that's not, just because someone states something doesn't make it true. So fake news, but it doesn't have to be intentional either.
Okay, you're trying to see the validity of your information, though it's represented as a vector. Oh, cool. So this is a very challenging question, I guess, because there are many models out there, like even on Kaggle, that are trying to like differentiate between news. And how they do it is that they try to find URLs that are related to news that actually produce fake news. Like, for example, the New York Times is always going to be legit. That's how people, that's the reputation of New York Times. But when you think of posts like Onion and etc., they're generally filled with fake news. So they try to streamline the content in the URL and they say that it's fake news. But coming to your question that can you look at a representation and say that it's true to the information or not, I think the best way to find how valid this information is, probably find some relevance between your information and the corpus presented to you and see if there's any similarity or see if there's more relevance. But it's highly sensitive to the data that you feed in. It's like knowing a perspective about a person from a third party. Probably the person's nice to you and it's not nice. He's not nice to another person. So it's sensitive to the data that you feed in. But if you want to see if it's universally true, so you're probably taking the information from different sources and you see how relevant it is to the maximum number of sources. Probably that'll make sense.
I have no information about artificial intelligence. I have an learning institute, and I want to try and start a course. It's an established institute since 1982 for young kids, ages 9 through 12. Do you have any recommendations of how one can start that?
Oh yeah, so recently this summer had this opportunity of teaching machine learning to middle schoolers, and so the first class was kind of challenging because I took like ready-made slides from Fast AI and I'm like, okay, here's logistic regression, this is SVM, but nobody actually gets it, or probably people expect differently because that age group is more imaginative than us. So I think the best advice would be that to not start with math, but try to see how math can be related to an equation. So they come in with hope saying that, oh my God, I'm going to design Jarvis or something, but it's not how it is. So instead of starting linear regression by saying, hey, this is an equation of a line saying y is equal to mx plus c, just be like, say you have like good data, bad data, and you're trying to separate it. So
do you have any recommendations of the books or something?
There's, I think the YouTube videos that I followed, I'll probably like upload to this website, so you can download it from there. It's like machine learning for dummies, but it's more simply explained.
The dummy describes me very well.
I mean, I'm not saying dummy, but it's basically trying to say like, so if you're trying to explain machine learning to people who do not know, I try to relate it with math and analogies. So, and this whole process, the YouTube links that I'll probably share are gonna extrapolate information from analogies rather than
just
complicated
to
math.
add to her point, actually, I've seen one group in California, a nonprofit. They're doing similar stuff, and they're getting 9 to 12 graders in the Valley area. So I think there are tons of information online. We can take it offline, and I'll try to post some information. But this is definitely a good start.
Yeah, it's actually useful because I think math is very complicated and everyone's scared of math, so am I, but it's really nice to know that how math can be used to make money. So yeah. Cool.
Anything else from the presentation, or just general interest in this area that you can?
I actually have a question. You talked about obviously having to ingest the information, and I can imagine a lot of those documents come in paper form, depending on the client that you're working with.
Yeah.
Do you all have significant issues with that kind of phase, turning it, paper to electronic? Or
So the most of the information that we receive are in the form of PDFs or in the form of CSVs, but we have faced a similar issue last year where they have, so when you're trying to like model something, you rely on historical data. And all these companies that have historical data, they have information from decades. Like the other time we got information from a customer of a scanned PDF, which was actually written using a typewriter. So if you're trying to analyze that information, the information is wonky, the tables are like skewed, and a part of it is completely non-readable for a human, so you can't expect a machine to learn that. So we generally have like pre-processing methods to clean up the data before we make it more structured. So yeah.
Okay.
Yeah, I have a question about, I see you build a model with RNN.
Mm-hmm.
So when I build a model, there are a lot of algorithm out there or models. So how do I know there is only the RNN good? Because a lot of algorithm with the model. So when you build, what are the bases you figure out RNN by direction text? How do you, that's my question. Yeah.
So, well, whenever you have, so this is how you map your data to a model. You, see, your data is the king. So try to understand what your data wants, and then you pick a model. Like, you try to use RNN or LSTM when you have sequential data. So when you have series of information, you're trying to do process of elimination to pick a model. So when you have like sequential information, you're like, okay, cool, my top candidates are RNN and LSTM. Tell me what is going to be better or like best suited for my model. Then you're going to try RNN, like a basic RNN model, and just see how it goes. Try to have an evaluation metric. Then use an LSTM and see how it goes. Then compare the evaluation metric. But the point that I'm trying to say is, from a perspective of not just a basic deployment, but when it goes into the bigger picture, like if it's a part of a product or it's being deployed or a customer's using it, the fact that a model that can be, so how do you evaluate a model? It's based on performance, not just accuracy. So when you can find a model that's super accurate, it's still good, but if it can perform quickly in an accurate direction, that's the most useful. And LSTMs work better than RNN in that case, because if you're trying to deploy on a larger scale, it has long-term memory saves, and it has memory gates to save that information, and RNN fails at that. But RNN is still good. It depends on the sort of data you have. Like if you have like small amount of data to make a prediction, use RNN. You have large amount of data and you want to remember relevancies, like the Avengers example I said, probably you need to know Avengers 1, 2, and 3 before the final one. So it gives you that long-term assessment of things. And it also helps in the vanishing gradient problem. So it's a implementation issue.
So I'm very curious how some of these applications like summary and abstract applications that are out there, how does those algorithms work? Because it's not just recognizing tokens, but also getting some sense and the relevance or importance of the content and then putting it in a very compressed or limited text. So any idea of anything that you can share of how those algorithms work?
So yeah, as I mentioned, Autoencoder does the compression. So what it tries to do is the math behind it. So when this is the part where it's boring, but it actually makes sense, is that you have a neural network where each neuron is connected to a next layer neuron, and you have like a combination of weight matrices, and you apply an activation function, and you get the next output. So point being, you are trying to get a value of compressed vector based on a sequence of mathematical operations. And I don't have the math slides in this, but for example, this one, you see those blue dots? It's basically saying that each layer is a neural network and the dimensionality is decreasing sequentially, and at each layer trying to apply some activation function. Activation function is how, for example, as a human, when we're trying to make decisions, it's like we're getting information and we're applying the human decision-making function to it so that it gives you a result. So that sort of non-linearity in math is called an activation function, and that's how it proceeds forward. Does that answer the question?
Not very sure. So, I mean, very simply put, I mean, let's assume there's a document of, let's say, 100 pages, and it's kind of a story or report on something.
Mm-hmm.
And now you see a small abstract of, let's say, 10 lines.
Yeah.
So how does it reduce that 100 page into 10 lines, and where it still needs to make some sense, right?
Yeah.
So
that is when you have, so the compression comes from a model like Autoencoder. So it summarizes like 100 line to 10 lines. And it's not that it's reducing to 10 lines, it's about picking the right words that are in that 10 particular lines. And the way those 10 lines are structured is using a language model, like probably like BERT or sequences or something of that sort. So you have a language model in place, you have a model just to do summarization, and you have like an ensemble of these two models.
Okay. Thank you.
Hi, I have a question. It may be a little off topic, but I'm more interested in AI where there's not existing big data to use all these algorithms. So I just want to get your opinion, so I don't want to take you off topic. But let's say that I had this idea that I wanted to create AI and replace somebody, for example, like a real estate agent. Okay, and now there's MLS data that you can mine, and you could do that, but you can't really, you don't have clean data that makes the decision of what an agent does. So you'd have to create new data, and then you would have to learn from that new data model. I guess that's at least how I'm understanding your presentation and how you would go about creating something that doesn't exist.
So,
do you have any comments?
Yeah, that is actually complicated because the whole thing is that machine learning can embrace they can help the person in place to make a decision, but they cannot eliminate the human in the loop. But it can definitely be like, say, a real estate agent takes like 10 minutes to analyze the property value. A model can do it, be like, hey, dude, this is going to be just like X amount of dollars rather than whatever you're thinking. It's going to give you an optimum range. So how it's going to take into account that it's going to use past data. It's going to be like probably in like 2001, this property was sold for that, the inflation was so-and-so, and the real estate area. And it's going to take a lot of features to make that prediction values. And speaking mathematically, you have like different models right now that take in features of a large dimension, even messy features, and predict a value. Like you have light GBMs, you have XGBoost to make a prediction. And this prediction, the value that comes out of this entire model, the output of it, will be super helpful for a real estate agent to make a decision. So maybe you cannot eliminate the real estate agent, but you can definitely help him, because it can make a decision in future based on past data, but there's so many unfactored challenges or like issues in the whole game that you need to have a person in the loop. For now, advancement in technology is not there where you can eliminate a human. Like it's also a sort of surety, because for example, we have flights in today's world where it's completely efficient to take off and land, but as a morality thing, people would not fly in a flight without a person, right? So even when you have real estate agent in the loop, probably there's someone just to be like, okay, maybe that's good, maybe that's wrong, but that clearance is going to be final by humans, say. Sure.
Okay, I think we have run out of all the questions. Thanks for coming in, and thanks to
Thank you all for coming in.
A nice presentation. Thank you. And we have some extra pizza and stuff. Please see if you can make use of it, or I will have to dispose, but help yourself. Thanks for coming. Hope to see you in the next one.